Hello, my name is Erik. I am a PhD student at Michigan State University, and today I'm going to how to quantify the shape of plants using topological data analysis. This is a cool project that mixes a bit of math, a bit of image processing, a bit of machine learning, and some plant biology. So what's TDA in the first place, topological data analysis? Think of it as a pipeline. We start with some raw data. I will mention a lot of X-ray CT scans of barley panicles in this case, but you can also have point clouds, time series, other kind of images. And then you have a bunch of topological tools, topology being the mathematical discipline that studies shape, and all those tools and methods aim to go from the subjective idea of shape to a much more abstract definition of morphology, or in other, that is a collection of numbers that mathematically summarizes the shape. And once you have numbers, you can do standard analysis and machine learning to try to see interesting patterns in your data. So by data, I mean the cross-composite II experiment, again, barley, which is a really cool experiment from the late 1920s when Harry Harland and Murray Martini collected 28 different varieties of barley, 20 different parents, F0s, from 28 different parts of the world, from very disparate climates, all the way from North Africa to the Everest and everything in between. They brought them to California, they took all the possible hybrids, that's F1, they self them F2, and then they put each of these F2s in its own piece of land, in its own plot, and let nature be nature, and just collect how the following generations look like, all the way to 58 generations. So this is an experiment of evolution in real time, and we are interested in keeping track on how actually the morphology changes from generation to generation. So to do that, we first need some images. So we have this 5-ton lead box in the basement of the plant biology building, and with some image processing, we can obtain this beautiful 3D reconstruction of barley panicles, and we can go even an extra leg and get individual seed images, 38,000 seeds in total. All these images are later aligned, so they have the exact same orientation, and we can measure their shape in a traditional way, like volume, height, width, length of each of these seeds. And we already see interesting patterns, like the seeds are getting longer and wider and bigger as generations go by. So that's already interesting, but that's not the full picture. For instance, you have this crease, you have this valley, and you are not measuring that. How does that change? Well, we turn to topology, to the Euler characteristic. So the Euler characteristic is this very simple number. So you have your image and you just measure the number of vertices minus the number of edges plus the number of faces. Maybe that number is too simple. So we want to see how that number changes as we chop or slice our seed in a lot of directions. So to see that in a picture, imagine that we have this seed and we chop it left to right, and then front to back, and then top to bottom. And as we keep chopping the seed, obviously all these quantities are changing, and we are measuring those changes. And finally, we put together all that in a very long vector. Now that makes sense, the Euler Characteristic Transform, because in 2014, it was mathematically proven that this collection of numbers, when you take into account all possible directions, all possible chops, mathematically summarizes all there is to know about shape. So how do we go about using this tool? Let's set the following goal. We have, again, 28 different barley accessions, and we want to classify them solely based on their grain information, and we have more than 3,000 grains. So we can describe the grains in 3 different ways, either traditionally, like lengths, widths, heights of each seed, and we can classify with 55% of accuracy. Not bad, considering that we are doing 28 things at a time. Then we can take chops on the Euler characteristic and reduce dimension, and suddenly we can now do 74%. We can classify with 74% of accuracy, even better. But that's not the end of the story. We can then combine both descriptors, both traditional and topological information, and that combined signature, that combined descriptor, gives us up to 86% of classification accuracy. So topology definitely is measuring something that we are missing with traditional descriptors. Can we say something about which of the directions or which of the chops is the most significant? Actually, we can do cross-Kalk-Wallis or ANOVA. And we can see that most of the interesting directions comes from top and bottom, which corresponds precisely to that valley, to that crease that we see on the top of the seed. So now that we are convinced that these descriptors, the topological descriptors, help us to understand the shape of the founders, can we do the same to understand the shape of the progeny? And we can measure the shape of the seeds in the F18 and the seeds on the F58 on the future generations. And turns out that in the future generations, essentially all the seeds resemble either 3 accessions, either Mason Carré, Atlas, or California Maru, and the other 25 are slowly vanishing. And the really cool thing is that our collaborators in UC Riverside, where they have access to all this barley, they are performing the same task but using RADSeq, and they are coming to similar conclusions to us. So topology actually helps us to understand all the fine details of morphology. And I'm more happy that I want to thank all my collaborators, and of course, thank you for being here. And I'm more than happy to answer more